Hi everybody, welcome to class today. Today we're going to be talking about energy in our chemical reactions, but there's going to be a lot of terms that you need to make sure you learn so that you can make this unit more understandable for you. The first one is energy, and we're going to define energy as the ability to do work or produce heat. And that means that we're going to be looking at all of the potential and the kinetic energy in a system. Now, the system is going to be known as our chemical reaction, and this total internal energy is going to be defined later as the enthalpy of the system. So when we refer to enthalpy of the system, you're going to be able to refer to it in that manner. So our potential energy is going to be the energy stored in the bonds, and the kinetic energy is going to be the energy of motion, which is going to be the kinetic energy of the vibrations within those bonds. And if you have, you'll have more kinetic energy based on the state of matter of that particular kind of reactants and products. Okay, so our next part. Our law of conservation of energy, which is very much just like our law of conservation of mass. Energy can neither be created nor destroyed, only transferred and changed. In other words, we're going to keep the energy of the universe constant. We're just going to use the energy for different applications. And you'll know this in physics as your first law of thermodynamics. We're going to be using terminology like temperature and heat. And when we refer to heat, we're going to refer to Q. And it's going to be in units of joules. When we refer to enthalpy, we're going to be referring to heat constant at a constant temperature, or a heat content, excuse me, and that's going to refer to both the total amount of potential and kinetic energy of the system. Now we have different terms, as you're going to be able to see here, that refer to the types of enthalpies that we have. So we might have an enthalpy of reaction, which is just the overall heat that is absorbed or released by a chemical reaction. We might have the enthalpy of combustion, in which case the reaction is a burning reaction. We will have an enthalpy of formation. Now for this one, you are going to want to make sure that you take in and memorize this definition. And for that reason, part of our notes will go over this definition. So here we go. This is going to be the heat absorbed or released when 1 mole of a compound is formed from its elements in their standard states at room temperature and pressure. So that means a compound is formed from its elements. And what we mean by standard states is solid, liquid, or gas. And so in other words, oxygen would always be a gas at room temperature. We also have some enthalpies of fusion, which is the enthalpy of melting, and the enthalpy of vaporization, which is obviously liquid to gas. For this class, we are going to be referring to the system as the area of the universe we are focusing on. In other words, the elements in the chemical reaction. The surroundings is everything outside those elements and compounds of the reaction. When we are referring to how much heat is either absorbed or released, we're going to be referring to endothermic and exothermic reactions. Things that are important here is that this is going to be a net absorption of energy for endothermic, and energy is going to be a reactant, and we would expect Q and delta H to be positive. When we have exothermic, that's going to be a net release of energy. Energy would be recorded as a product, and our net overall Q, which can be converted to delta H, is going to be a negative number. So it turns out that there are several steps in most chemical reactions that lead to this overall change in energy. And it doesn't really matter what the state function terminology is trying to say. Is it doesn't really matter what the steps are. The overall change in energy is going to remain the same here. Okay, so we're specifically going to be talking today about the calorimetry or Q equation. Q is equal to mc delta T, where our heat Q is going to be in joules, and our mass can either be in kilograms or in grams, but that's going to be dependent upon what our specific heat constant is, whether that's joules over grams degrees Celsius or kilojoules over grams degrees Celsius. Sometimes this will even be written as kilojoules over kilograms degrees Celsius, or it'll be written as joules over kilograms degrees Celsius. So you're going to need to pay attention to that unit label. And then we're always going to calculate our delta T as final temperature minus initial temperature. And so that's going to be how we're going to use that equation. So let's go ahead and see if we can relate that to some actual examples here. So our first example says, if I burn 0.315 moles of hexane in a bomb calorimeter containing 5.65 liters of water, what is the molar heat of combustion of hexane if the water temperature rises? So the heat capacity of the water is 4.184 joules per grams degrees Celsius. It could also be written as 4,184 joules per kilograms degrees Celsius. So let's go ahead and see if we can make this into something that is understandable. Our first thing that we're going to have, oh, I don't want it to do that. Let's change our size of our writing here. The first thing that we're going to have is our mass. And so our mass is written as the mass of the water, because we're using the chemical equation and the reaction to heat some water. And so we have 5.65 liters of water, and we're going to have to remember that mass is not in liters, it's in grams or kilograms. So we can also convert that to milliliters, so 5,650 milliliters, which that's important because then I can multiply that by density, which is 1 gram per milliliter, which is going to end up giving me then grams of 5,650 grams. So yay for that. We've got our mass. Remember, our equation is Q is equal to mc delta T. Okay, so our next thing that we want to be able to use is the C, or the specific heat of water. And so you'll notice what I have is two different choices here. So I'm going to go ahead and use the one that has grams and joules in it. So I have 4.184, and that's unit label joules over grams degrees Celsius. You are going to have to pay attention to unit labels in this, otherwise you're going to get yourself going in the wrong direction. Our delta T is actually given to us as a total temperature rise of 55.4. That would be like to say that our temperature started lower and it ended up rising to a higher temperature. So that means we have everything that we need. So we're going to calculate Q by taking our mass, 5,650, and multiplying it by our specific heat constant, which is 4.184, and multiplying that by 55.4. When we get our answer, we're going to get Q is equal to 100, I think it comes out to, 984, I believe, no, 434, excuse me, 34, and that's a lot of joules. So if we convert that to kilojoules, we come out to 1,310 kilojoules. Now, that's all great and all. That's our Q. Remember, Q is the heat, and it asked us not for heat. It asked us the molar heat of combustion. Molar heat of combustion is what that asked us for. So that's the same as asking us for this enthalpy. And so did you notice that this problem gave us moles? So that means to find the delta H of combustion for hexane, we are going to take the 1,310 kilojoules, and we are going to divide it by 0.315 moles. And when we get our math, and I'm going to pause myself so I can do my math real quick, and then we'll come back and get our answer. Okay, so I had to make some changes. The actual Q came out to 1309634 joules, which still rounds to 1310 kilojoules. And then when we get this math right here, we come out with 4,159 kilojoules per mole. And the unit label comes out to kilojoules per mole. Now, why didn't we just keep it at heat? Because it asked us for the molar heat of combustion, which is also known as the enthalpy of combustion. And so that's why we had that last little part we had to add on to it. Okay, so let's take a look at another example here at the bottom of the page. Okay, so it says, if I burn 22.0 grams of propane in a bomb calorimeter containing 3.25 liters of water, what is the molar heat of combustion of propane if the water temperature rises 29.5 degrees Celsius? Okay, so in this case, we are going to have to keep two different masses the separate. So this particular mass right here, that one is going to give us the thing that we're going to use to calculate moles. And so our moles for that one is going to be, because that's going to be the thing that causes the temperature to rise in the water. So we're going to do 22.0 divided by the molar mass of C3H8. So that's going to be 12 times 3 is 36 plus 8 is 44. So that's going to come out to our total number of moles is 0.500. So everybody, that's a point right here, by the way. Okay, so that's our moles. Our mass of our water is going to come out to 3,250 grams of water using the same format I did last time and converting liters to milliliters and then converting milliliters to grams using the density of water. Then I'm still going to have my specific heat constant, which is still going to be 4.184 grams. Let's see. No, that's going to be joules per gram degree Celsius. There we go. Sorry, everybody. And then we have our total temperature rise of 29.5 degrees Celsius. Okay. And so then we're going to multiply these things together in the format of Q is equal to M times C times delta T. And so we're going to have 3,250 times 4.184 times 29.5, and I'm getting 401,141 joules, which kilojoules is going to come out to 4,011 kilojoules. And you already know we're going to have to divide by the number of moles, which is 0.500, which is going to give us 8,022 kilojoules per mole. All right, so that's a good example of some of the types of calculations that IB is going to ask you to do. So we need to make sure that we are talking about specifically this idea of enthalpy, because I've shown you a little bit of calculation already. You are going to be paying attention to Q, at least in calorimetry problems, but ultimately you're going to be using those then to calculate an enthalpy, whether it's an enthalpy of reaction or an enthalpy of combustion, as we've seen in these last two. Just like heat, enthalpy is a if it's greater than, let me make sure, yep. If it's greater than 0, then we have endothermic. In other words, heat is being used in the reaction or absorbed. If it's less than 0, then heat is released as a product, just like we have done before. That is not a surprise there. Okay, so then we're going to go on to some of the way it's used in graphs. So the idea being here that this is showing you the entire set of reactants and products and how they change. And you'll notice that if we have a exothermic reaction, the products have less energy than the reactants. So heat has to have been lost as energy as a product, lost. If we have more products having more energy than reactants, then heat has to have been being gained. So if the products are lower than the reactants, that's exothermic. If the products are higher than reactants, that's endothermic. And you're going to be able to tell that by calculating delta H. So in the lower products, lower than reactants, your delta H should come out to negative. And in the products higher than reactants, your delta H should come out to positive. And so we have some examples and terminology here for you to make sure you look at. And I think we have already talked a little bit about delta H in moles, but I'm going to save that conversation for later. So at this time, that is the end of your notes for today.